Welcome to week 6, Center of Gravity and Centroid. Today we're going to cover only part 1, which deals with calculus. Yay! So first, the center of gravity is very intuitive. It's basically the point on a body where all of the mass passes through it. So for a square, it'd be completely at the center. For a triangle, it would be a third up. For a ring, it'd be at the center once again. So here we're going to use formulas to locate the center of gravity of an area. And the center of gravity is basically the point where, for example, here you put the pencil and you put it at the exact center of gravity and the object balances. So that's what we're trying to find. So some important things to remember are notations. Okay, so if we look at y bar, this I'm going to call y bar and x bar. The bar represents the location of the center of gravity of this entire body. When we have y squiggle or x squiggle, I'm going to call it squiggle because I don't know what this is, like the official term for this little squiggly thing. So x squiggle, y squiggle, z squiggle, that is the center of gravity of a differential element within the entire body. So we pick this little element within the body, and its center of gravity is y squiggle, x squiggle, z squiggle. So that's the difference. You'll notice later. So to find the centroid of an area like this represented on an xy plane, we refer to calculus. So we draw in little differential elements within the area, and we use integration over the entire x dimension or the entire y dimension to find the center of gravity of the overall body. So here are the equations. So x bar, the center of gravity in the x location of the entire body, is the integral of x squiggle dA over integral of dA. And same thing for y. And once again, this is important. We need to remember that x bar and y bar are the coordinates of the center of gravity of the entire body, whereas x squiggle and y squiggle are the coordinates of the center of gravity of the differential element. And dA is the area of the differential element. So you'll see, we're going to do an example. So here we have this area in an xy plane, the shaded blue. We want to determine the centroid, x bar, y bar, of the shaded area. So the first thing that I do, these are just the formulas that we need to use in the future. So the first thing that I do is I draw my little differential element right here. And I label everything. So I label a point xy because this is located on the curve, and so this is going to be some point xy. And I label dy, so this is the differential length of the element. And then I label x squiggle and y squiggle. X squiggle and y squiggle are the center of gravity of our differential element. And because our element is a rectangle, it's obviously halfway down the rectangle, right? Intuitively, we know what the center of gravity of a rectangle is. So then what we have to do is express x squiggle and y squiggle in terms of x and y. So if we look at y squiggle, it's located basically here, right, up from the x-axis, and it is the same as just simply saying y. So y squiggle equals y. But when we look at x, so x is here, x squiggle is going to be half of x. So it's half the distance of x. So it's x over 2. And then the differential area of the element is x. So x times dy. So that'll give us this entire area. And then what else we know is that we're given that y equals x cubed and x equals y to the 1/3 if we rearrange that. So now all we have to do is plug into our formulas to find x bar. I go from 0 to 1. Now the reason I go from 0 to 1 is because I'm differentiating in terms of dy, and y goes from 0 to 1 as well. So 0 to 1. Then x squiggle, we said x squiggle was x over 2, so I plugged that in, and times dA, we said dA was x dy. Over the integral 0 to 1 of dA, which was x dy. Now, because we're integrating in terms of dy, we need to make sure that all of our terms are y. So every time I see an x, I use this relationship, x equals y to the 1/3, and I end up with y to the 1/3 everywhere I have an x. So then what do? I just go on and do calculus, simplify, right? Then I take the integral, and once I take the integral, I end up with x bar equals 0.4 meters. So I found one part of my center of gravity. Now I need to find y bar. Same thing as y bar. So here, y squiggle was just y, and dA was x dy. So I end up with this equation, and now we're still integrating in terms of dy. So once again, for wherever I see an x, I need to substitute y to the 1/3. So I do that, run through my math, do the integration, and I end up with 0.5714 meters y bar. So what does that mean? If we look at this finally, we found that our center of gravity of this area is x equals 0.4, so 0.4 is somewhere around here, and then y equals 0.57, so let's say 0.6. So our overall center of gravity is going to be 0.4 and then up 0.6, so it's going to be somewhere over here. So that's how you find the center of gravity. Pretty straightforward as long as you know and remember how to label everything. So let's look at another example pretty quickly. I'll let you guys do it on your own. Here I draw my differential element once again, but here instead of being a horizontal element, it's a vertical element. So some things change a little bit. So we have this differential distance dx, and then we have, once again, on the curve we have a point xy, and we have our x squiggle, y squiggle, which is the typical center of gravity of a rectangle. So x squiggle is, in this case, equal to x, right? Because x squiggle is located here, but so is our x. Y squiggle, in this case, is located half of y. So y is here, but y squiggle is here, so it's y squiggle equals y divided by 2. And then our area in this case is y times dx. That'll give us its length times width, so that'll give us this differential area. And we have y equals x cubed, so x equals y to the 3rd. So once again, I just take in all of the things that I just determined, plug them into my equation. Because I'm differentiating in terms of x this time, I need to make sure that every time I see a y, I substitute my x cubed, run through it, I end up with 0.8 meters. I do the exact same thing for y bar. Every time I see a y, I plug in my x cubed, and I end up with 0.2857 meters. So finally, x center of gravity is 0.8. I would say 0.8 is about here, and then y is about 0.3. So 0.3 is about somewhere. So the center of gravity would be somewhere around this point right here. So that's how you find the center of gravity for an area along the xy axis.